Everyone has heard that space is freezing. But freezing what? Space is almost empty. There is no icy wind, no cold air pressing against your skin, and almost nothing for a thermometer to touch. So if an astronaut floated from sunlight into shadow, would they freeze instantly? Or could the same empty space actually make them overheat? Here is the strange answer. Space is not simply hot or cold. An object in space can burn, freeze, or do both, depending on one invisible battle. To understand that battle, we first have to ask a surprisingly difficult question. What does temperature really measure? In everyday life, temperature describes the matter around us. Air is made of particles. Those particles move, collide, and carry energy. In a simple gas, higher temperature means the particles have more average kinetic energy. Lower temperature means less. When warm air touches your skin, countless particles transfer energy to you. When cold air touches you, your body transfers energy to them. But remove almost all those particles and the familiar idea of air temperature begins to break down. That is the problem with space. Different particles can have measurable temperatures. Radiation can have an equivalent temperature. An astronaut, a satellite, and a moon rock can each have their own temperature, but empty space itself is not a giant ocean of cold air. And that creates our first major reversal. A place can contain extremely energetic particles and still fail to warm you. Imagine one racing grain of sand hitting your hand. It might carry plenty of energy, but one grain will not feel like a hot wind. Now imagine trillions of slower grains striking you every second. Together, they can transfer far more energy. Temperature tells us something about energy per particle. Heating also depends on how many particles arrive, how often they collide, and how much energy they transfer. Space has very few particles. Even when those particles are individually energetic, there may not be enough of them to deliver much heat. This is why asking, "What is the temperature of space?" is incomplete. We also need to ask, where are you? Are you in sunlight? What material are you made from? Which direction are you facing? And how quickly can you release energy? Because in a vacuum, heat plays by different rules. On Earth, heat usually moves in three ways. Conduction happens through direct contact. Touch a hot pan and energy moves into your hand. Convection happens through moving fluids. Warm air rises, cool air falls, and currents carry energy around a room. Radiation travels as electromagnetic waves. This is how sunlight crosses nearly empty space and warms your face. In the external vacuum of space, there is almost no gas for convection and almost nothing touching an isolated object for conduction. A spacecraft can conduct heat through its own structure, but it exchanges heat with the outside, mainly through radiation. This is why a vacuum bottle keeps a drink hot or cold. The empty layer between its walls suppresses conduction and convection. Space behaves like the most enormous vacuum bottle imaginable, but there is one enormous heater shining through it. At Earth's distance, direct sunlight delivers roughly 361 kilowatts of energy to every square meter facing the sun. With no atmosphere to scatter that energy and no moving air to carry it away, a sunlit surface can become dangerously hot. Move the same surface into shadow, and the incoming sunlight disappears. The object continues emitting infrared radiation, so it begins losing energy and cooling. The moon demonstrates this brutally. In full sunlight, parts of its surface can reach about 127 degrees Celsius. In darkness, temperatures can fall to around -173 degrees. Same moon, same surrounding vacuum, a difference of roughly 300 degrees. The vacuum did not choose either temperature. Sunlight, shadow, material, and time determine the result. So an astronaut could have a hot sun-facing side and a much colder shadow-facing side. And this is where Hollywood usually reaches for the ice effect. No, an unprotected astronaut would face an immediate medical emergency, but not because the body suddenly turns into a block of ice. With almost no surrounding matter, the body cannot lose heat through cold air. It mainly loses heat by radiation and by moisture evaporating or boiling in the low pressure. Those processes take time. The far faster danger is the vacuum itself. No breathable oxygen and almost no external pressure. Loss of consciousness from oxygen deprivation would arrive long before the whole body froze solid. Real spacesuits are therefore not just warm clothing, they are tiny spacecraft. They supply pressure and oxygen, shield the astronaut from radiation and micrometeoroids, and actively remove excess body heat. In fact, while working hard inside an insulated suit, overheating can be as serious a problem as cooling. Now for the strangest example of all. A region above Earth can reach thousands of degrees and still fail to keep you warm. High in Earth's thermosphere, individual gas particles can absorb enormous amounts of solar energy. Temperatures can reach around 2,000 degrees Celsius or even higher. That sounds hot enough to destroy almost anything. But the gas is unbelievably thin. There are too few particles colliding with you to transfer heat the way dense hot air would. NASA describes this as the heat that won't keep you warm. This separates two ideas we often confuse. Temperature describes the energy state of matter. Heat is energy being transferred. A sparse gas can have a very high temperature while delivering very little heat. Meanwhile, direct sunlight can transfer large amounts of energy across a vacuum without needing hot air at all. So why do people keep saying deep space is about -270 degrees Celsius? Because one famous number is both correct and misleading. The universe is filled with faint microwave radiation left over from its early history, the cosmic microwave background. That radiation has a blackbody temperature of about 725 Kelvin, roughly -270.4 degrees Celsius. This is often called the temperature of space. But it is not the temperature of imaginary air. It describes the weak background radiation arriving from every direction. An isolated object far from stars would emit its own heat into space. As it cooled, the energy it radiated would decrease. Eventually, if the cosmic background were its only important energy source, it could approach a temperature near that background. But real objects are rarely that simple. Starlight, reflected light, planets, internal electronics, radioactive materials, and even the object's surface color can change the balance. Black surfaces absorb and emit radiation efficiently. Shiny reflective layers absorb less sunlight. Orientation matters. Rotation matters. Distance from the sun matters. In space, temperature is not a location label. It is the result of an energy budget. Spacecraft engineers therefore do not simply insulate against cold. They control where energy enters, where it travels, and how it leaves. Reflective multi-layer insulation reduces unwanted radiation. Heaters protect components that become too cold. Conductive paths spread heat through the structure. Radiators face dark space and release excess energy as infrared light. That final part is easy to miss. Spacecraft cool themselves by glowing in wavelengths our eyes cannot see. The International Space Station uses large radiator panels and circulating fluid loops to move heat away from equipment and crew. The James Webb Space Telescope takes the hot versus cold problem to an extreme. Its 5-layer sunshield separates the sun-facing equipment from the shaded telescope. Across those layers, the temperature difference is approximately 299 degrees Celsius. Both sides exist in nearly the same region of space. What changes is their access to radiation. The shield does not create cold. It blocks incoming heat so the telescope can radiate its own heat away. So, is space truly freezing cold? Not in the ordinary sense. Space has particles and radiation that can be assigned temperatures, but vacuum is not cold air. It does not pull heat from you by touch. It removes two familiar heat transfer paths and leaves objects to trade energy mainly through light. That makes space more dangerous, not less. In sunlight, you may absorb energy faster than you can release it. In shadow, you may radiate energy away with little coming back. The outcome depends on balance. So the better question is not, how cold is space? It is, what is heating you and where can that heat go? And if empty space is not really a freezing wind, what would actually happen to a human body during the first 60 seconds without a spacesuit? That is a much stranger story, and the next boundary fact-bound can cross.